1. It should be co-prime to 3k sub n plus 1. And moreover, it should be congruent to 1 modulo 3 sub dm prime. This is a tricky condition because if you take a divisor, let's say a primitive divisor or something that's built up of primitive divisors of the polynomial phi sub n evaluated in the integer a, where a, let's say, is an integer bigger than 1, then you get for free that those guys are 1 mod n. But we don't want them to be 1 mod n. We want them to be 1 mod 3n. So we want a little bit more than n. And this is why this condition is a bit tricky. Well, suppose that you have identified such a divisor. Then you can construct the next number. And here's how you construct it. You take the number d sub m prime, which participates in here. Then you take capital dkm divided by d sub m prime plus capital d minus 1 divided by 3dm prime. Now, what you have to notice is that these guys are integers because dm prime divides km. D is 1 modulo 3dm prime, so this ratio at the end is an integer. Also, d is an odd number because they come from cyclotomic divisors of this. So the first expression is odd and the second expression is even because since d is odd, d minus 1 is even, and you're dividing into an odd number. So this guy is an odd integer. Furthermore, this odd integer, if you do this calculation, is bigger than k sub m. Since it's bigger than k sub m, it's a new integer. And I have to prove to you that it satisfies the required congruence. Well, why does it satisfy? Well, 3km plus 1, we know that it divides 3 to the dm prime plus 1. And the divisor d, because of the condition I, it's a divisor of this cyclotomic polynomial in 3, which also divides 3 to the d sub m prime plus 1. And I have the condition that these two numbers are co-prime. Since they are co-prime, it means that their product divides into 3 to the power d sub m prime plus 1. But what is their product? Well, let's expand d over. We write 3k sub m plus 1 multiplied by d is 3k sub n d plus d. I write d as d minus 1 plus 1. And then I factor out d sub m prime. And I obtain the number that I called k sub m plus 1. So this number, 3k sub m plus 1 times d, it's actually equal to 3 times the next member in the sequence, k sub m plus 1, plus the number 1. And it divides 3 to the dm prime plus 1. And the last step is to notice that dm prime is a divisor of k sub m plus 1, and k sub m plus 1 is odd, and so is dm prime. So because of this, it means that 3 to the d sub m prime plus 1, which was a multiple of 3k sub m plus 1, it's a divisor of 3 to the power k sub m plus 1, which is what we wanted. Well, that's what we wanted, modulo proving that assertion about the cyclotomic polynomial of index 2dm prime evaluated in 3 containing such a divisor. Well, for this, I'm going to assume further that d sub m is a multiple of 3 squared times 5 squared, which I will see that for k sub 1 it works, and it will be propagated into k sub m by induction. In particular, 3 divides d sub m prime, and d sub m prime over 3 is odd. Remember, d sub m prime is a multiple of d sub m. And I'm in a position to apply a theorem of Schinzel. What Schinzel proves, so there are these things called Luca sequences, whose general formula is like a to the power n minus b to the power n divided by a minus b, where a and b are co-prime integers. For us, we are looking at a equals 3 and b equal 1. So for us, the Luca sequence is 3 to the power n minus 1 over 2. A primitive divisor is a prime factor that appears at level n, and it didn't appear before. So it's a prime factor of 3 to the n minus 1 that did not divide 3 to the m minus 1 for any m smaller than n. What Schinzel proved that under certain hypotheses, not only that you get a primitive divisor, because that's the celebrated primitive divisor theorem, which for Luca sequences with real roots was proved in 1913 by Carmichael, and for Luca sequences with complex conjugated roots was proved only in 2001 by Bilois, Roy, and Voutier. But work of Schinzel from 1963, for example, he wrote a sequence of papers, and the one that I'm citing there is the first one in the sequel, in which he proves that under certain assumptions, not only you get one primitive prime factor, but you can get 2, you can even get 4, you can even get 6 in some cases. For us, we only need 2 of them. And there's a paper by Yurichevich of 2009, which completes basically what Schinzel did. Because Schinzel in 1963, he said, oh, if n is sufficiently large, then there's at least two prime factors. But he didn't say what sufficiently large is. This was done by Yurichevich, where he showed that sufficiently large, you can take a number around 10 to the 12, and it's already sufficiently large for all the examples. So this is what we are going to do. So this is now you'll have to bear with me because I'm going to define some notation and I'm going to take that result from Schinzel a bit like a black box and I'm going to show it. So the sequence is alpha to the n minus beta to the n over alpha minus beta. The pair alpha beta equals 3, 1. What Schinzel does, he defines various parameters in there. For example, the parameter L is the square of the sum between alpha and beta. These alpha and beta don't need to be integers. They could be complex, they can be conjugated integers in a quadratic number field. So you can start with some quadratic equation and you look at the roots and you can even take maybe the square root of that. So, and you obtain lemma sequences. So anyway, so for him, the parameter L is equal 16. The parameter M, which is the product, is 3. Then he takes this number, which he denotes zeta, which is capital M times the maximum between L minus 4M and L, which in this case is 48. He writes 48 as a square times the square free, and he denotes the number kappa to be the square free part after you wrote the square. So 48 is 16 times 3. And then according to this number kappa, according to its residue class and so on, he has another parameter which he calls eta. And for our case, eta is equal to 2. Now you take these notations and he looks there, he takes a number little n, which for us is 2dm prime. He takes a number called nu, which is the radical of n, the product of distinct primes in n. He takes a number L, which is a half of it. And he takes the number capital N, which for us it's also the radical of that. And little m equal kappa equal 3. So L over m is odd. M is odd, n equal to L. He even has some number delta, which is equal to 1. So anyway, you go through all that. And here is what he gets. What do you read out of his theorem? With all these parameters for us, you take the cyclotomic polynomial evaluated in the number n at 3, of index n at 3. But n is composite, and it even has prime factors at powers larger than 1, because for us, the number n is 2 sub dm prime, and we saw that that's divisible by both 9 and 25. So what you can do, you can write it as the cyclotomic polynomial of basically the radical of that number, evaluated in 3 to the power, the number divided by radical, which in our case, it's going to be big. It's at least divisible by 15, because as I said, little n is divisible by 9 and by 25. And then this number, he proves that it's canonically splits into two integers. And the way it splits into two integers, he takes these primitive roots of order n that participate into the cyclotomic polynomial, and he groups them in a certain way. He says, well, for us, this number n is a multiple of 3. Therefore, these roots have to be co-prime to 3. So he takes those roots which are co-prime to 3. He even puts I there, which is the square root of -1. And then he groups them according to whether the power, once you wrote that root as plus minus I times something to the power s, he's wondering whether that s is 1 mod 3 or is 2 mod 3. So the ones which are 1 mod 3, he puts them in this factor. And then he groups them, the ones which are -1 mod 3 there, and then he switches around the signs. And he proves that these two numbers are integers. That's a fascinating paper. And each one of these integers somehow contains primitive prime factors. And this is how he gets to the conclusion that there should be at least two primitive prime factors. Because what might happen, it might happen that, for example, just because you have the cyclotomic polynomial evaluated in number 3, it doesn't make any prime factor there necessarily primitive. Because, for example, if you evaluate it in any integer, 3 to the power, let's say in an even integer, let's take even a power of 2. The cyclotomic polynomial corresponding to, let's say, 2 to the power k, it's x to the power 2 to the power k minus 1 plus 1. And if you evaluate it in x equal to 3, you're going to get a power of 3 plus 1, which is an even number. So that even number doesn't count. What the theorem says that there might be some spoof prime that's there, but that spoof prime is at most the largest prime factor of n. It's certainly a divisor of n. And then after you have removed that, everything that's left is primitive. And then Yurichevich proves, he does the calculation, and he proves that Schinzel's argument work for, let's say, n at least 1.2 times 10 to the 10. So this is how he gets about 2 prime factors. Then we said, oh, okay. Now suppose now that phi1 and phi2 have primitive prime factors. And this primitive prime factor, let's assume that they are co-prime to 3km+1. We will prove later that this is so. Then any divisor which is a product of primitive prime factors, it's also co-prime to 3 to the power km+1. If 3 to the power dm prime plus 1 has at most 2 primitive prime factors, let's suppose that it has at most 2 of them, then this means that at least one of these guys, phi1 or phi2, must be a prime, because if none of them is a prime, then one of them is going to have 2 primitive primes in there. As I said, there might be a spoof prime that's not primitive, which is going to go with one of the 2 factors, but the other one is going to catch at least 2 primitive prime factors. So let's suppose that it has at most 2 primitive prime divisors, and one of these guys is already a prime. So I'm going to show that this prime works. Why does it work? It is congruent to 1 modulo 2 dm prime. But remember that I want it to be congruent to 1 modulo 3 dm prime. So let's go back and look at it. This number, like this factor, what does this number have? What's the property of it? It is basically, if we expand it, it's an algebraic integer, which as an algebraic integer is congruent to a root of 1 modulo a very large prime power of 3. So what I can do, if I can prove that this root of 1 is 1 itself, and if I can prove that this very large power of 3 is bigger than the power of 3 that appeared in dm prime, then I am already set. And this is basically the calculation. You look at this root of unity, then you see that each one of the factors contains phi of L over 2 of those values, because they are phi of L values in 1, 2 up to L, which are co-prime to L. They are all co-prime to 3. And then half of them are 1 and half of them are negative 1 because of this involution map. If I take S, which is co-prime to L, then L minus S is also co-prime to L. L is a multiple of 3. This involution changes 1 mod 3 to 2 mod 3. So there's half of them which are 1 mod 3, and the other half which are 2 mod 3. And how even is phi of L? Well, L is divisible by 15. So H divides phi of L. So phi of L over 2 is a multiple of 4. So if I go over here and I look at this calculation in here, I get that the last coefficient has to be 1. And so I get what I want. I get that any one of these factors is congruent to 1 modulo a large power of 3. And how large is that power of 3? Well, suppose that A is exactly the power of 3 that divides dm prime. We said that A is at least 2 because dm prime is divisible by 9. 5 squared is divisible by dm prime. Then this number, little n over capital N, is divisible by at least 15. 3 to the power a minus 1 times 5. So even if I half it, I still get a large enough number, bigger than 3 to the a minus 1, which is greater or equal a plus 1 for all a greater or equal to 2. So this shows that if a was the exact power of 3 in dm prime, then this primitive prime, which I'm assuming that it's primitive, it's congruent to a larger, to 1 modulo a larger power of 3, and it's also 1 modulo dm prime, so it's congruent to y modulo 3 dm prime. This is one of these guys if there were at most 2 primes. Well, if there's at least 3 primes, the problem is much easier. Suppose that I have 3 primes which are all congruent to 1 modulo dm prime. So let's write them as some numbers, L sub I dm prime plus 1. If one of these L sub i's is 0 mod 3, I'm done. Check, because I already got a factor that's 1 modulo 3 dm prime. Suppose that none of them is a multiple of 3. Is all 3 of them are the same mod 3. Then you just do this calculation in here and you get that the product of them is 1 modulo 3 dm prime. Then you say, okay, what's the only case that's left? The only case that's left is that none of them is 0 mod 3 and 2 of them are different. But if 2 of them are different, then their sum is 0 mod 3 because the 2 different ones must be 1 and 2 mod 3. So I multiply those 2 guys and again I get that. So somehow I say, oh, okay, maybe I have everything I need now. I can take dm prime equal km. Then I take a primitive prime factor of 3 to the km plus 1, which is congruent to 1 modulo 2 km, and cannot divide 3 times km plus 1, because this is an even number. So all odd prime factors in it should be at most 3 km plus 1 divided by 2, which is smaller than 2 km. So the coprimality condition is fine. Also, if km is bigger than 1.2 times 10 to the 10, then I can continue. So the only issue now seems to be that k1 is 3 squared times 5 squared times 17. It's too small. It's not bigger than 1.2 times 10 to the 10. Well, let's just do a calculation. I calculated for him. D1 is 3 squared times 5 squared. It works. I take D1 prime equals D1 equals 3 squared times 5 squared. I take this polynomial in here, which becomes phi of 2 times 3 times 5 of 3 to the 15. I asked Mathematica is divisible by this prime, which is, I guess, 697,381,651. And this prime is congruent to 1 modulo 3d1 prime. So I can take capital D equal to this prime. I can construct the number K2, and now K2 is correct. K2 is big enough, and from here on, everything works out. And what you have to notice that this condition about divisibility with 3 squared times 5 squared persists, because dm divides dm prime divides km plus 1, because km plus 1 was built involving primitive prime factors of this one. So therefore, dm divided dm plus 1. And since d1 was already a multiple of the square of 15, it means that the square of 15 divides dm for all m. I haven't checked if it works for all the other values, but I would assume it works for all the other values, because you see what was needed in this argument is not really how that number looks like. What it's needed that maybe that number is odd, is divisible by 9, so you can get a 3. Maybe it's divisible by some other square of a prime, because then when you look at these powers of 3, which are supposed to be 1 modulo dm prime, you can catch an additional factor of 3 in there. Okay, what about replacing 3 by some other integer a bigger than 1? If you replace a by 2, then you get 2k plus 1 is 1 modulo 2k plus 1. And actually here I can play the prime game, because I can take p equal to k plus 1 to be a prime, and the above congruence becomes 2 to the p minus 1 over 2 is negative 1 mod p. What this signals is just that 2 shouldn't be a quadratic residue modulo p. So in particular, p should be 3 or 5 mod 8. So I get the set of primes of density 1/2. Actually, this works for every even number. What do I mean that it works for every even number? Take a to the power k plus 1 congruent to 0 modulo ak plus 1. Take ak plus 1 to be equal to p, so I get k is p minus 1 over a. So what I want a to the power p minus 1 over a to be negative 1 mod p. As we saw in the example with a equals 3, the reason it doesn't work is because if a is odd, if you exponentiate this one, you get a contradiction to the Fermat's little theorem. But if a is even, you don't really get that. What you do get, you get a calculation inside this field. So you take the field by the Chebotarev density theorem. You take a field which contains a to the power 1 over a and contains some appropriate roots of unity. And then what you say, you take a prime number with the property that p is congruent to 1 mod a. Then when you look at a to the power p minus 1 over a, this one is a legitimate number, and it has to be congruent to a root of unity. So then the root of unity should be a root of unity of an even order. So then it's, let's say, some root of unity e to the 2 pi I k divided by a, and then you just say, okay, let k to be an odd number, or something like that, instead of, so as to be a number which is not necessarily co-prime to a, but it should have an order of 2 inside it, which is much smaller, which is smaller than the order at which 2 divides a. So this argument, for example, in not always, because you can start with the number a equals 16, and then you believe that 16 to the power 1 over 16 is an algebraic number of degree 16, but it isn't, because it's 2 to the power 4 over 16, which is 2 to the 1/4. So actually the field is smaller. And then you don't have to adjoin roots of unity of order 16. You can adjoin roots of unity of order 4. But for the case in which, for example, a is square free, then the density of such primes is exactly 1 over 2 phi of a. So the phi of a, you get it from the prime number theorem in progressions. P should be 1 mod a. And the half, you should get it because these roots of unity should give you that number. When a is equal to 2, for example, you recover the result from the previous page. And maybe in the last 10 minutes, 15 minutes, I'll give you an upper bound. So the upper bound, it's basically, this is how the upper bound, it always ends up in those kind of problems. If you work with things, for example, Carmichael numbers, pseudo primes, and so on, when you have some sort of a congruence, which involves some value in the exponent, then you either have possibility that the value in the exponent can be a prime, And if that is the possibility, in most cases, you're going to get a positive proportion of primes because of those primes usually are Chebotarev primes that sit in particular conjugacy classes in some extension of Q, like in the previous example. But if you don't get primes, then you get functions of this kind. You get something much smaller than the primes, because the primes are x over log x, and the log is the exponential of the double log, and this one is x over the exponential of a constant square root of log double log. So this would be the last result that I will show you, and I will give you a proof of that. So basically, because A is odd, again, you get the phenomenon that you cannot have ak+1 to be a prime. Indeed, this is the same argument as in the proof when A was equal to 3. If ak+1 is the prime P, then K is P minus 1 over A. You translate the congruence in terms of P, you get A to the P minus 1 over A is negative 1 mod P. And since A is odd, you can exponentiate that, and you get a congruence contradicting Fermat's little theorem. So ak+1 is composite. So let me look at numbers of the form capital N equal ak+1. So I find it more suitable to count those integers. So instead of counting integers k up to x with the property that a to the k+1 is divisible by ak+1, I'm going to count numbers capital N, which are 1 modulo a. So they are 1 plus a times k, where after I subtract 1 and I divide by a, that number k is suitable. So it satisfies if you want a to the power n minus 1 over a is minus 1 modulo n. And then the way we do it, a lot of those arguments proceed like this. What you say either the largest prime factor of this number is small, and then you get something that's called a smooth number, and the smooth numbers are understood. You know about their counting function, or the largest prime factor is big. But if the largest prime factor is big, then this congruence in there forces the largest prime factor to be somehow determined in few ways in terms of the quotient, and there you get an extra saving, and you have to balance between these two savings. So I'll take a y, a function of x, to be determined later. So now I'm going to count numbers n up to x, or let's say a times x, such that the largest prime factor is at most y. And it is known that this is modeled by some function, which is called psi of xy. And psi of xy is basically a positive proportion of x. The positive proportion is given by something called the Diekmann function. And the Diekmann function in the input u decays at the speed 1 over u to the u. And u is the ratio between log x and log y. Since here I modified a little bit the x. It's not my initial x, it's ax plus 1. But once you take logarithm, the logarithm of ax is the same as logarithm of x as you go towards infinity. So I can just replace in this calculation, whenever I see the ones, I can ignore them. And I can say, okay, I have roughly the proportion u to the power minus u. And to be correct, I'm putting a little o of 1 in there, so you cannot complain, because if I don't put the little 1 in there, it's not correct what I'm saying. But if I put the little 1 in there, then it's fine. So from now on, I want to count n, which are up to x, which are 1 mod a, and such that the largest prime factor of them is at least y, where y I don't know yet what it is, but I'll find out later, such that if I put little k equal n minus 1 over a, then it passes my congruence. So I exponentiate to power a, I get a to the power capital N minus 1 is minus 1 mod a. Now what I'm going to want to replace this, sorry, this is a mistake here. This shouldn't be a, should be capital N. So what I want to keep it, instead of keeping the full congruence modulo capital N, I want to keep the congruence only modulo capital P, where P is the largest prime factor of N. Modulo capital P, a to the power P, I can replace it by a, thanks to Fermat's little theorem. So a to the capital N is a to the capital Pm, which is a to the m mod P. Therefore, a to the capital N minus 1 is little a to the power m minus 1 modulo P. But I also know that a to the power capital N minus 1 is minus 1 mod n, because of this congruence, which is minus 1 mod P. Therefore, a to the power m minus 1 is minus 1 mod P. In particular, P has the property that it divides a to the power 2 times m minus 1 minus 1, and little m is not 1, because we know that the number capital N is not prime. And that's what's going to restrict P. So now P is a large prime, which has the property that it divides this expression. So somehow, if you give an m, little m, the number capital P is determined in few ways. And let's see how we do it. Well, what we can do, here is again a little error. This capital P shouldn't be there. I take an argument which is originally due to Erdős and Murty. So maybe even older than that. So what they show, suppose that you count primes with the property that the order of 2 modulo those primes is small. And by small, I mean it's somewhere below the square root of the prime. So let's fix ourselves at p to the 1/3. Then an argument of Erdős and Murty shows that the number of such primes is very small. It's at most p to the 2/3. So the way they prove it, they say, well, P has to divide a number, which is of the form 2 to the power k minus 1, where k is at most t to the 1/3. Let's say you count primes up to t. Now you multiply all these expressions together, 2 to the k minus 1 for all the k's ranges from 1 up to t to the 1/3. So you get 2 to the sum of these exponents. The sum of the numbers up to t to the 1/3 is t to the 2/3. And the product of all those primes must divide this expression. Therefore, the number of them is at most the exponent, because each one of them is at least 2. And that's how you get this bound. So now you can just split it according to these two possibilities. Then you say, let's suppose that I'm in the first possibility. I have the first possibility that the largest prime factor is at most p to the 1/3. Then I have this counting function here. But my number, capital P times m, is at most x. So capital P is at most x divided by m to the 2/3. So I said, oh, okay, so let's sum this up over all the m's. But how far can m go? It can't go all the way to x, because m times p is at most x, and capital P is at least y. So m can only go up to x over y. So it becomes x to the 2/3. You integrate 1 over t to the 2/3 up to x over y, and you get a saving. The saving x divided by y to the power 1/3. And then you say, let me go to the other situation. In the other situation, I have that 2m minus 1 must be 0, because remember that the order of p divides this expression. Therefore, the order of p divides 2 times m minus 1, and the order of p is large if I'm in the second situation. So this means that m should be 1 modulo this order. Well, I have to sacrifice this 2 or something. So let's fix p greater or equal to y, and let's count m's, which are up to x over p, which are congruent to 1 modulo the order of 2 modulo p. So those numbers are in this progression. They are up to x over p, and they are congruent to 1 modulo this order. So the number of them is x divided by p times this order. Normally, you have to add 1 to it because of the first term of the progression. But for us, the first term of the progression, m equal to 1, is not allowed. So you can just write this. And now this order is at least p to the 1/3. So this puts the amount of m's. Their counting function is at most x divided by capital P to the 4/3. And now you sum this one up. When you sum this one up, you can forget about p being prime. You're just summing up the series 1 over n to the 4/3, but you don't sum all of it. You sum up its tail, starting with y, and its tail starting with y. You approximate it with this integral, so you get x over y to the 1/3. So in some sense, this argument that looks kind of silly is optimal in the sense that it obtained x over y to the 1/3 for both branches. So what do you have to match now? You have to match the smooth numbers, which had a proportion about u to the u. You have to match them with a proportion y to the 1/3. And u was log x over log y. So now you just solve this equation and see what you get. You get u to the u, sorry, this should be plus, not minus. You want u to the u to be y to the 1/3. You take logs. It becomes u log u equal 1/3 log y, but u is log x over log y. So you say log x over log y times some double log. It's 1/3 log of y. So now you understand that if you put log of y here, this means that log of y squared is about log of x times double log of x. And then you have to play around with the constants to understand what happens with this 3. Because here log of y is about square root of log x. So there's another half coming from there. So anyway, you solve this. You get log of y is root 3 over 2, roughly, times square root log x double log x. But remember, you have to divide by the exponent 3. So this is why you get 1 over root 6. And I'm sure this argument is not optimal. You can probably do much better. You can probably get x divided by the exponential of log divided by double log instead of the exponential of square root log double log. But it already shows that they are much fewer than the primes. The sum of the reciprocals is convergent, and so on and so on. So although it's an infinite set, it's not a very thick set. We have the lower bound of log x. We have the Schinzel argument that says even if you start with 3825, you get some other infinity. But that Schinzel argument, it's not clear how fast those things grow. They probably grow much faster than the powers of 3. So although you get additional elements in this sequence, it's not clear that those additional elements would contribute in a substantial way to getting a better lower bound on the counting function. And I will stop here. Thank you very much.
Thank you, Florian, for a lovely talk. For those of you who were suspicious, sometimes we really do have number theory in the number theory seminar.
Okay.
So, any questions for Florian?
There's a comment in the chat.
Okay.
Carl has a question.
So, can you hear me?
Yes, I
Yes.
can hear you.
Hello.
Yes. Hi, Carl.
I think that if you have a number A, sorry, K, in your set K sub A,
Yes.
the thing that you're counting in your theorem,
Yes.
then AK+1 is a pseudoprime base A squared.
Ah.
So in the case
Oh, I
A,
see. Because you square it and you get rid of the -1.
yeah, and you
I
can
see.
just tie into theorems about the
Okay.
distribution of pseudoprimes.
That's
And-
great. Thank you for improving that.
Right. So it
So
gets
is that what I said? X divided by the exponential of log x divided by double log x?
I think it's log x divided by triple log x.
Oh, I see. Because that's a function you usually denote capital L of x in some of these papers, right? Or is that the exponential of log divided by double log?
I think it's like the distribution of Carmichael numbers.
Okay. All right, we'll look into that. Thank you.
You're welcome.
Florian, can you close your screen share?
Sure.
Now everyone's visible again. Good. Other questions about this curious exponential congruence problem? So I have to thank Paolo Leonetti, who asked me in the chat whether I was recording, and I said yes, because I was recording. But then when I double checked, I wasn't recording. So we have the whole talk recorded, except for maybe the first 15 minutes. So
That's right.
so no one will ever know what the problem is that you were talking about, but they'll see proofs of things.
Mm-hmm.